So I'm going to do a really short video showing how to derive ordinary least squares in linear algebra form. So let's get right into it. We need to start with the idea of writing down an equation for a line. So we have our usual coordinate system, x and y, and to make our life really confusing, I'm going to notate each point as a vector, see the boldface, a vector x, right? What is that vector x? Well, each one of those vector x's, demonstrating a single point, has got two components. The first component is a constant 1. The second component is the actual x-coordinate on that axis. Okay, so x of 1 has this x value in its second component, and it has the number 1 in its first component. This x2 has that x value, whatever it is, plus the number 1 in its vector components. Why do we put that constant in there? Well, it enables us to bring the intercept into the linear algebra. Okay, we don't have to have a separate b term. I personally prefer this notation. You can, of course, just throw that notation out and have a completely separate b term, a completely separate intercept. But it looks like this. So if we have a constant term in there and the actual x-coordinate here, then our weights to describe the parameters of this line, well, we know that the parameter of a line is slope times x-coordinate plus the intercept. So then our weights look like this. The bias term is the first element, and the slope is the second element. So b plus mx can be written as the vector x transposed times the vector w. Now, why is it transposed? Well, just a reminder, this is going to tell you the first element in a matrix multiplication is going to be how many rows. Well, we want one single number out. We want a scalar out. So when we transpose x, it becomes a one row vector. So that's how many rows is one row. And then the second element of a matrix multiplication, right, tells you how many columns. So one row, one column. The output is a single scalar number. And we're calling that y hat. Remember, y hat is the estimate, the estimated y, the value that our line is trying to predict given the x inputs. It's always worthwhile remembering that this kind of regression says, given an x, what am I predicting for a y? Okay? So, how do we go from there? Well, these predictions have a certain amount of error, shown here in the blue. So the actual y-coordinate of this point, we're going to denote y sub n. The predicted y-coordinate, that's what this line of regression is. It's a prediction, right? That's y hat sub n. So the error between those two is the actual minus the predicted, which turns out to be a function like this, right? We can just substitute in the linear algebra, and it's x transpose w. Now, important here, what we have formulated is just per data point. For x1, what's error 1? For x2, what's error 2? And so on and so forth. The next step is to take this into a complete matrix form. What does I mean by that? Remember this thing called a design matrix? So we had a slide on this earlier. What that means is, right, this is the vector for x1. This is the vector for x2. These are transposed vectors, so they're row vectors. Okay, which means that it looks like this. So it's going to be 1s going down, and it's going to be x1, x2 going down. Again, just to remind you, boldface x are vectors, not boldface x is the x-coordinate. Okay? So this is our design matrix. Now, here's where the magic happens. We can have all of the data points we've got at once in this setup, where we have a boldface prediction vector, y hat, which is the prediction of all of our training data points. And that is going to be our design matrix X, right? We don't have to transpose now because do you see that the transpose already happened? So X is going to determine how many rows, our design matrix X. And the number of rows is going to be the number of data points. So we know y hat is going to be a columnar vector that's got as many predictions in it as we have data points. Okay? So no transpose necessary this time because we have already transposed it. And so that's going to be all of our outputs, right? That's going to look like this. Actually, I guess I should keep with my color scheme. That's supposed to be a hat. Y hat 1, y hat 2, dot, dot, dot. Okay. A columnar vector of predictions for every data point. Okay, great. That means that similarly, we can define a vectorized error, which is, of course, is going to be exactly the same thing, right? It's going to be our vectorized predictions minus xw. I forgot to actually boldface this the last time. Okay, so that's super. Now we've got all of our errors and we've got all of our predictions in one go. Oh, and I suppose just to make clear, sorry, I apologize for the pause. I just realized that my cat was outside and it was chucking down rain, and he was very sad. All right, so he's back in now. Right, so error 1, error 2, dot, dot, dot. All right, brilliant. At this point, we can start to say, what should the loss function be? We've got all the mechanics now. What should our loss function be? How should we decide what is the best possible line of regression? Because I want to note for you one important aspect. All of these things, they are parameterized by the weights. So where the line is of course parameterized by the weights. That's just about the definition of what we're trying to do, right? But the errors are also parameterized by the weights. Oh, good. I completely hosed that, right? Good job, Jason. This. Did anybody yell at me while I was doing it? You should have. This is the actual y coordinates vector, right? All of the y's. I hope you caught that and you were yelling at the screen. All right, brilliant. So again, we have our errors. One could easily imagine that our loss function is that we want to set up a line that minimizes those errors. And this is called the residual sum of squares. So the residual sum of squares is the idea that these e's, right, this e vector, those are called the residuals. And what we want to minimize is the sum of the square of all those residuals. All right, so to minimize the residual sum of squares, what it's saying is that our loss function is going to be, I'm going to get rid of the color notation now, by the way. Okay, I'm just tired of that. So this is the vector E. That is the same as saying sum up for all of the data points right? Those are equivalent statements. So this is the linear algebra format for it. And this is kind of the algorithmic. Take every one of these e's, square it, and sum it up. So how does the linear algebra do that? Well, when we transpose the column vector, it becomes a row vector. And so the row vector, the first element in the matrix multiplication, determines how many rows. And the second element determines how many columns. So one row, one column, we get a scalar number, right? And it effectively does this. All right, at this point, we are ready. This is our loss function. This is the thing which, again, it is a function of the w's. So it is the thing that we are trying to minimize. So we've got all the machinery. This preview is done. We will pick this up in class. Thank you so much. Bye for now.